Okay. So, okay. So just to finish our discussion of the heat equation, I mentioned in the last class the Schroeder estimates, right? Which were estimates on Holder norms of solutions to what's called the Poisson equation, Laplacian of u equal to f, with some boundary conditions. So similarly, there are Schroeder estimates for the heat equation. So suppose we have this following initial value problem. So we have a domain D in Rn, a bounded domain with smooth boundary. Then we look at the cylinder. D sub t is D closure cross 0t. And we're given the following initial data. So the following data for this problem. So f is say a smooth function on this cylinder cross mapping to R. Pi is a function on the vertical sides of the cylinder, so on boundary D cross 0t to R. And psi is a function on the, you think of it as a function on the bottom of the cylinder from D closure to R, okay? So the initial value problem for the heat equation is the following problem, that the heat operator, Laplacian minus del del t applied to U, this is equal to f of xt, okay, for xt in the cylinder. And the initial conditions are at time 0, u of x0 is equal to the function psi of x, okay, for x in D closure. And the boundary value conditions are, for any time t, the value of u at the boundary for xi, a boundary point, is equal to capital phi of xi t. Okay. So why am I taking this data? Because you can see that by the parabolic maximum principle, if a solution to this initial value problem exists, then it is unique. Why? Because, so here's my cylinder. And this initial condition gives me the value of a solution on the bottom. And this boundary condition gives me a value of a solution on the vertical sides. Okay. So if I have two solutions to this initial value problem, then say U1 and U2. So if I subtract U1 minus U2, then Laplacian minus del del t of U1 minus U2 will be 0, right? Because both of those are equal to f. So you'll get f minus f, which is 0. So U1 minus U2 will satisfy the heat equation, del U del t equal to Laplacian. And the boundary conditions will become 0, right? So you'll get a solution to the heat equation, which is 0 on the parabolic boundary. That is the bottom union the vertical sides. Therefore, by the parabolic maximum principle, it is less than or equal to 0. And then you consider minus u, minus of the same solution. So that will also be a solution to the heat equation, where the boundary conditions on the parabolic boundary are also 0. So minus u will also be less than or equal to 0. So you will get u is equal to 0. Okay. So therefore, U1 is equal to U2, where U1, U2 are any two solutions of this initial value problem. Is this clear? Yeah. Okay, so that's why this set of initial conditions and boundary conditions, this is an appropriate set of conditions for this solution, so that you get a unique solution. Is that clear? Yeah. Okay. So so what one wants to say is that given this initial value problem, you have a solution to the heat equation satisfying these three conditions. The only thing one has to make sure is that there are certain compatibility conditions between the initial data. So for example, between this function psi and the function capital phi. So if I look at time 0, right, then if I take a point on the boundary xi in boundary D, then what is psi of xi? That is u of, this should be a xi here. So u of xi comma 0. Let me change that. This will be u of xi comma 0. And u of xi comma 0 by this third condition, this is also equal to capital phi of xi comma 0, right? So a necessary condition for a solution to exist is that psi of xi is equal to phi of xi 0 for xi in boundary D. Okay. Now there's another necessary condition, which is that if I calculate the Laplacian of psi at a boundary point xi, right, then this is the same as the Laplacian of u at xi comma 0, right? Because at time 0, psi is equal to u. And if I use this first equation, then the Laplacian of u I can write as del u del t plus f at the point xi comma 0, right? And at time 0 on the boundary, u is equal to phi, capital phi. So del u del t will become del capital phi del t at xi comma 0, right? Plus f of xi 0. Okay, so we get another compatibility condition. Laplacian of psi at xi, a boundary point, is equal to del phi del t psi 0 plus f of psi 0, right? Okay. Is that clear? Yeah. So these are conditions between psi and phi, right? So these conditions have to be satisfied for a solution to exist, right? Is that clear?
Yeah, that's
Yeah, that's fine. Yeah. Okay.
Sir, I have a question.
Yes.
So I joined late. I actually didn't know the class starts at 11. So can you just give an overview of what you just said right now?
Oh, yeah. So I'm considering this initial value problem on the cylinder. So I have a domain D in Rn, right? Okay, let me just do it from the top. So D is a bounded domain in Rn with smooth boundary. And then I'm looking at the cylinder. dt is D closure cross 0t. Okay, so this is the cylinder. And then I have the following data. So f is a function on dt on the whole cylinder. Phi is a function on the lateral boundary of the cylinder. That means on boundary D cross 0t. So that's this part here. This is boundary D cross 0t. And psi is a function on D closure. So that you think of as the bottom of the cylinder. That's D closure across 0. Okay. And then I want a function on the cylinder u, which satisfies the partial differential equation Laplacian minus del del t, that's the heat operator applied to u, equal to f of xt in the cylinder. And I have an initial condition at time 0, u of x0 is psi x. And I have a boundary condition at any time t, u of xi t is phi of xi t. So that means I'm specifying the values of my solution on what we call the parabolic boundary, right? That means the bottom union the vertical sides. Okay. So this, why is this a good set of conditions? Because this guarantees that any solution, if it exists, is unique. Right? Because if I take any two solutions, U1, U2, the difference will satisfy the heat equation del U del T equal to Laplacian of U, right? By subtracting, by applying delta minus del T to U1 minus U2, I'll get F minus F, which is 0. And also the boundary conditions of U1 minus U2 will be 0. So I'll get a solution to the heat equation which vanishes on the parabolic boundary. Therefore, it's less than or equal to 0. And then applying the same argument to minus u, you'll get that it's greater than or equal to 0. Therefore, it is equal to 0. So therefore, the two solutions u1, u2 are equal. Okay?
Yeah.
So if this problem has a solution, then it's unique. And there are some necessary conditions for this to have a solution. So if I take a boundary point psi, then psi of xi has to equal capital phi of xi 0. And also Laplacian of psi at xi has to equal del phi del t at psi 0 plus f of psi 0. Okay?
Yeah,
right?
yeah, got it. Yeah. Thank you.
These necessary conditions are just matching up the boundary conditions, right? I mean,
Correct, correct.
at the floor of the cylinder with its
Correct.
mass.
Yes, correct, correct. Yeah, these are just matching up the boundary conditions. Yeah. On the boundary of the cylinder. Correct. That's right. Yeah. Okay. Yeah, that's right. Okay. So then the theorem is, so, okay. So, all right. One can define Holder spaces in two variables, okay, for the cylinder. So I'll do this again later in the course. I don't want to, the definition is a bit long, so I don't want to spend time on that. I'll just say that you can define Holder spaces of functions. So there's a Holder space C2 plus alpha, comma 1 plus alpha by 2. So essentially this means you have two space derivatives, two continuous space derivatives, which are alpha Holder. Okay. So all the space derivatives of order 2 are continuous and alpha Holder. Okay. And you have one continuous time derivative, which is alpha by 2 Holder. Okay. This turns out to be the right class to look at. So you have this for the whole cylinder dt. And so what will happen is you want a solution U which belongs to this Holder space. And your data F should belong to the Holder space C alpha comma alpha by 2 in the cylinder. Your data psi should be in C2 plus alpha of the domain D closure. And your data phi should be in C2 plus alpha of the boundary D cross 0T. Okay. So let me just check this is correct. So, sorry, 1 second. Sorry. Yeah, okay. Fine. So then what we get is, so if these compatibility conditions, so let me call them double star. Okay, so then the theorem says that if the compatibility conditions double star are satisfied, then there exists a unique solution U to star such that so we have the following Schroeder estimate. So the C2 plus alpha 1 plus alpha by 2 norm in dt, this is less than or equal to a constant C times the C alpha by 2 norm on dt of f plus the C2 plus alpha norm of psi plus the C2 plus alpha norm of phi. Okay, where C is a constant, which only depends on the domain D, the dimension N, and the exponent alpha.
So sir, in the norm of phi, where you have written the norm phi C2 plus alpha, there should be 2 exponents of C, right? Because phi is in 2 variables, right?
Phi, it is in 2 variables, but yeah, so in the lateral surface, I'll have to check what is the exact definition. Yeah. It is, but the dimension of the lateral surface is also n. Okay. So
basically, you are saying
let me just check.
delta is
Okay,
more-
let me just check. Let me just check. Okay. Let me just check. Yeah, okay, okay. So, all right, fine. So, okay. Yeah, no, you're right. It's in the same space. 2 plus alpha and 1 plus half alpha. Okay, fine. So it's in the same space. Yeah. So phi will be in 2 plus alpha comma
And it
Yeah.
has to be the same 1 plus alpha. Because
1
you
plus
have
alpha.
taken one time derivative.
Yeah, right. It's just that the space dimension has gone down by 1. So that's all. Yeah. Yeah. So you're right. That's right. So
And in the norm of phi in the last.
that's the, yeah, 2 plus alpha and 1 plus alpha by 2. That's right. Okay. Okay. Yeah. Thank you. This is correct. Yeah. Okay. So the point is, if we wanted a solution to the Dirichlet problem, right? If we want to solve the Dirichlet problem using the heat equation, then what you do is for your data phi and psi, right, and f, there you take the heat operator applied to u. This is equal to 0. Okay, so that is your f. And then the boundary condition u at time 0 is some function psi, which is C2 plus alpha up to the boundary. And then u of psi t this you take to be equal, constant equal to psi. Okay. So this is just psi of psi. Okay. So if you want a solution to this, you have to check the compatibility conditions are satisfied, right? So the compatibility conditions, so this is my star, and my compatibility conditions double star are, so for psi in boundary D, I need that u of, so psi of psi, sorry, this below is capital phi, so this is capital phi. No, sorry, this is psi, this is psi. But I mean, this is equal to my, what I meant, this is equal to my capital phi of psi t. It's independent of t. Okay. So yeah, I have to check psi of psi is equal to phi of psi 0. And that is true because phi of psi t is equal to psi xi for all t. So this compatibility condition is satisfied. For the other compatibility condition, I need Laplacian of psi at xi. This should be equal to del phi del t psi 0 plus f of psi 0, right? So in other words, this right hand side, del phi del t will be 0 because phi is constant in t and f is 0. So this will be 0. So what I want is that the Laplacian of psi vanishes on the boundary, right? Okay. Now, actually, what was I given? I was given some function on the boundary, right? So all I have to do is extend it to a function in the interior such that the Laplacian at boundary points vanishes. Okay. So that one can always do if your function, suppose your function has a smooth extension. Okay. So suppose I have a G from boundary D to R such that G, well, you just need it to be actually smooth on boundary D. Okay. Yeah. So then you can always find psi on the closed domain, D closure, smooth, such that psi restricted to boundary D is equal to G, and Laplacian psi restricted to boundary D is equal to 0. This one can always do. So how can one do that? Well, yeah, so
The Poisson kernel, right? Convolute with the.
I see. What are you saying? Yes.
So convoluting with the Poisson kernel should give it, right?
No, I mean that I just want to see that will give you the solution to the Dirichlet problem, but that's a much more non-trivial result. We want to solve the Dirichlet problem using the heat equation, right?
Okay.
So we want to solve the heat equation using the Dirichlet, we want to solve the Dirichlet problem using the heat equation. So I'm not going to assume the solution of the Dirichlet problem. Okay. Rather, this one can solve in a more simple way. So what you do is you can locally you can flatten out the boundary. Okay. So you can flatten this out. To a horizontal strip. Okay. Right. So this will look something like a part of Rn minus 1 cross an interval. Okay. This is so. So this is yeah. So this is inside. Okay, so this part is, this is 0, this is say epsilon. Okay. And yeah, so let me just think a second. So if I want the Laplacian of, so I can define a function here on this rectangle. And so that will, the point is, when I look at the Laplacian here, that will, on the boundary, how should I say this? So, yeah. Okay, so, well, we can do this without flattening. I don't, well, okay. So we'll talk about tangent spaces later, but essentially the idea is that you have the tangent space to the boundary, and you have its orthogonal complement, which is one-dimensional. Okay. And the Laplacian, it turns out, you can write as a sum of second partial derivatives along an orthonormal basis for the tangent space to the boundary, and the second derivative along the normal direction. Okay. Now, the second derivatives along the boundary direction, those are determined by g, the function on the boundary. Okay, so that gives me some sum of second derivatives along the boundary directions. But then in the normal direction, I can choose this extension as I want, right? To make the second derivative in the normal direction, that should be equal to minus the sum of second derivatives in the tangent direction to the boundary. So when I sum up, then I'll get 0. Okay. Right. So that's not hard to do, right? I need to choose my psi in this normal direction just. Okay. So that the second partial derivative in the normal direction, that adds up with the partial derivatives in the tangent direction to give me 0. That's all. Okay.
So you do this computation at the boundary or like near the boundary?
Yeah, at the boundary. You can do it at the boundary. You
Okay.
can do it at the boundary. Yeah. You can do it at the boundary. So, I mean, look, I'm going to be doing the basics of multivariable calculus, so I didn't want to get into this too much because you need to use a bit of multivariable calculus. So, yeah, that's all. So, in order to say what the Laplacian is at the boundary, what are these second derivatives and so on. So, we can talk about that later. But if you grant this fact, okay, which is a simple, this is much simpler than the solution to the Dirichlet problem. Okay, this is a simple thing to show. You just need the Laplacian of the smooth extension to vanish on the boundary. That's all one needs for the compatibility conditions to hold. Then you get a solution to the heat equation with these initial value and boundary conditions. And then the Schroeder estimates will tell you in particular that the C2 plus alpha norm in the space variable, this is uniformly bounded independent of t, because this f term, this is 0. This psi term, this is a constant independent of t. And this phi term, this Holder norm is uniformly bounded because in the space variable, this is a fixed function of space, psi, right? And in the time variable, it's constant, right? So that will tell you that this Holder norm is uniformly bounded in time of phi. Okay, so the right-hand side is less than a fixed constant. So you get that the C2 plus alpha norms of U are for all time are uniformly bounded. And from that, the argument we did last time will tell you that U converges as time tends to infinity, U converges to a harmonic function with boundary value psi of xi, right? And therefore, you get a solution to the Dirichlet problem. Is that okay? Yeah. So this Schroeder estimate for the heat equation, for the parabolic equation, that can be used also to show uniform boundedness of the C2 plus alpha norms. That's all I wanted to say. To finish the discussion of the heat equation, this is all I wanted to say. Is that okay?
Yes, sir, it's fine.
Yeah,
fine.
it's yeah.
It's okay. Yeah, okay. That's all I want to say. Okay, so then let's now start from basics. Okay. So I'm actually going to start with some linear algebra basics. So okay. All right. So let's start from very basics. I'm going to be talking about tensor products, and we'll be using tensor products quite a lot in this course. So I just want to make sure we're all clear about tensor products. So first, a very basic proposition, something called the basis criterion, which you may or may not have seen. Okay. So suppose V is a vector space over a field K, and let S be a subset of V, then the following are equivalent, that S is a basis of V. And this is equivalent to the following: for any K vector space W and any function F from this subset S to W, this has a unique extension to a linear map. Okay, so there is a unique linear map F tilde from V to W such that F tilde restricted to S is equal to F. Okay, so one direction is clear, right? If S is a basis, then you can extend a function on the basis uniquely to a linear map, right? That's clear? Yeah.
Yeah, so you are assuming the finite dimension.
No, not at all. No. It's a Hamel basis. No finite dimensionality. No.
Oh, okay. All right.
Yes. No finite dimensionality. Every vector space has a basis by Zorn's lemma, right? Yes.
Yeah.
Okay. By Zorn's lemma, every vector space has a basis. So yeah, this is no finite dimensionality here. Yeah. Okay. Okay. So one direction is clear, right? And for the second direction, we have to show that if we have this sort of universal property that any function on the set S extends to a unique linear map, then we have to show the set S is a basis. So first we show that it's linearly independent. Okay, so that is quite simple. If I give you n vectors in this set S, right, then what we can do is we take the vector space K power n and we define a function on this set S, which takes the vectors v1 to vn to the basis vectors ei of K power n and say 0 otherwise. Okay. So then this F extends to a linear map F tilde, right? And F tilde maps these vectors v1 to vn to linearly independent vectors e1 to en. That implies that v1 to vn must be linearly independent, right? Because if I take a linear combination alpha 1 to alpha n such that summation alpha I vi is equal to 0, then I get that 0 is equal to F tilde of summation alpha I vi. That becomes by linearity summation alpha I ei, and the ei's are linearly independent. So therefore the alpha is a 0 for all I. Okay. So therefore any finite subset of S is linearly independent. So S is linearly independent. And in order to show that it's the span of S is all of your vector space V, what you can do is, since S is linearly independent, again by Zorn's lemma, you can always extend S to a basis B. So if the basis B is equal to S, then we're done. Otherwise, you define a function from this basis B to V, where V goes to V if V belongs to S, and it goes to 0 if V belongs to B minus S. So since B is a basis, we can extend this function on the basis to a linear map f tilde, okay, from V to V, such that f tilde restricted to B is equal to F. But then f tilde restricted to S is equal to the identity map of S, right? But S satisfies this hypothesis that any function on S extends to a unique linear map. So the identity map of S, it extends to the identity map of V, right? But here we're getting another extension of the identity map. So that also has to equal the identity map of V, right? By uniqueness of the extension, f tilde has to equal identity V, but f tilde restricted to the basis B minus S, by definition, this is 0. So that's a contradiction. Is that okay?
So if we assume that S is not a basis initially, wouldn't the first
Yes.
part give a proof by contradiction?
Sorry, I didn't understand what you're saying.
So if we are trying to prove the second part and we assume that it is not a basis,
Yeah.
no, we are trying to prove the first part and we assume that it is not a basis. And then that would imply that we can pick B1 be an element of S such that it's not linearly independent, and then we can get a contradiction, right? By
No,
what
no,
you-
no, no. If it's not a basis, it could still be linearly independent, right? It could be a linearly independent set which is not a basis, right?
Yes, what I mean is that if it's not a basis, then
Yes.
there exists a finite collection in it such that it is not linearly independent.
No, that's not true. That's not true. It could be a linearly independent set. No, that's not true.
Oh,
What you're saying is false. What you're saying is false.
could you define what a basis is for infinite dimensional sets?
Yeah, sure. It's a linearly independent set whose span is the whole vector space.
Okay, so if there's
Look,
an
even in finite dimensions, if I take the set E1, E2 sitting inside R3, that is a linearly independent set which is not a basis, right? So what you're saying is false in finite dimensions too.
okay, yeah.
Just linearly independent doesn't mean basis, right? It has to
Yeah.
span. It has to
Okay,
span
yeah.
the whole space. So that's what we proved in two parts. First, we proved that S is linearly independent. Second, we proved that S spans.
Okay,
That's what we did. Right.
yeah.
Well, we used S is linearly independent in order to prove that S is a basis. Yeah. Right. Just a set which is linearly independent is not a basis, right? It can
Yeah,
always
yeah.
be extended to a basis.
Yeah.
It can always be extended to a basis.
Okay.
Okay. Fine. So is this all right? This basis criterion? Yeah. Okay. Fine. So we'll be talking about tensor products. So those are, I mean, directly related to what are called multilinear maps. So you've probably seen the definition. So suppose V1, V to Vn and W are vector spaces over K. Then a map T from the Cartesian product V1 cross Vn to W. This is multilinear if whenever I fix one of the variables, then whenever I fix n minus one of the variables, then it is linear in the remaining variable. Okay. So if I take Vj's, little Vj's in capital Vj for j not equal to I, then as a function of the ith variable, from Vi to W, V goes to T of V1 to Vi minus 1, V comma Vi plus 1 to Vn. This is a linear map. Okay. So it's linear in each variable separately. Okay. So the set of multilinear maps from a Cartesian product to W, this itself forms a vector space, right? Because the sum and scalar multiple of multilinear maps is multilinear. Okay. pointwise sum and scalar multiple. So now we can define what are tensor products. So let V1 to Vn be K vector spaces. So a tensor product, we will define it in terms of a universal property. All right. So the tensor product of V1 to Vn will be a vector space E together with a multilinear map phi from V1 cross Vn to E, which has the following universal property. So if I take any other multilinear map from V1 to cross Vn to W, okay, where W is some other vector space, then this factors through the multilinear map from V1 cross Vn to E. So that means there is a unique linear map T tilde from E to W such that T is equal to T tilde composed with phi. Okay, so E was my tensor product of V1 to Vn. So it comes equipped with a multilinear map phi from V1 cross Vn to E, and any other multilinear map from V1 cross Vn to W, T, it factors through this space E and through this map phi, okay? So T can be written as the composition of a multilinear map with a linear map. So, I mean, the tensor product has the nice property that it reduces multilinear maps to linear maps. Okay. So this map phi from V1 cross Vn to E, this is called a universal multilinear map. Why is it a universal multilinear map? Because any other multilinear map T, it factors through phi, right? It is some linear map defined on the tensor product E composed with phi. Okay. So is the definition clear? So I won't go into the existence. You can look up the construction of a tensor product and the fact that it satisfies this universal property. Okay. It's not very difficult, but I don't want to spend time on that. So I'll leave it to you to look that up. Okay. But we will prove some facts about tensor products. So the first fact is that this universal property, it uniquely determines the tensor product. So in other words, any two tensor products, E and F, are naturally isomorphic. Yeah. So naturally means there are isomorphisms between them which don't require a choice of basis. Okay. So this will follow in a straightforward way from the universal property of tensor products. So suppose phi from V1 cross Vn to E and psi from V1 cross Vn to F. Suppose these are the two universal multilinear maps, okay, for the two tensor products E and F. Okay. Then if I look at psi, psi is a multilinear map from V1 cross Vn to F. So therefore, by the universal property of phi, psi factors through phi. So psi I can write as some linear map, psi tilde composed with phi, where psi tilde is a linear map from E to F. Okay. And similarly, by the universal property of psi, the multilinear map phi, it factors through psi, right? So phi I can write as phi tilde composed with F, where phi tilde is a linear map from F to E. Okay. So now consider the following commutative diagrams. So we have psi is factoring through phi, right? So psi is psi tilde composed with phi. Okay. And similarly, phi is factoring through psi. Okay. So using this, I can write psi. Psi is equal to psi tilde composed with phi. But phi again, I can write as phi tilde composed with psi. So if I substitute that here, then I get that psi is equal to psi tilde composed with phi tilde composed with psi, right? So what does that mean? That means that psi factors through psi with this linear map, psi tilde composed phi tilde. So we have this commutative diagram, psi going here, and then this is factoring through psi composed with psi tilde composed phi tilde. But psi also factors through psi with the identity map of F, right? But then in the universal property, when you factor through the map psi, the corresponding linear map is unique. Okay, that's part of the universal property, is that there is a unique linear map, okay, from the tensor product to the given vector space, so that you factor through that. So by uniqueness, psi tilde composed phi tilde has to be the identity map of F. Okay. Is this clear? This is by the uniqueness in the universal property. Okay. And similarly, you can show that phi tilde composed psi tilde is the identity map of E. So therefore, these two are inverses of each other. So they are isomorphisms. Okay. Is this all right?
Yeah, it's all right. Yeah.
Yeah, it's okay. It's just the uniqueness we're using in the universal property, right? We're using the uniqueness of the linear map through which you factor. Okay. So then now we have a unique tensor product, therefore, if it exists. So we're assuming existence of the tensor product. Okay. So now denote the tensor product by V1 tensor Vn. Okay. And denote the universal multilinear map by tensor from V1 cross Vn to V1 tensor Vn. The notation for this is V1 comma Vn goes to V1 tensor Vn. Okay. All right. So now we can use the basis criterion to prove the following. So let EI and Fj be bases of vector spaces VW. So I'm not assuming finite dimensional. These could be infinite dimensional. All right. Then if I look at the set of tensor products, EI tensor Fj, where I comma j belongs to capital I cross j, this is a basis of V tensor W. This is a basis of V tensor W. Okay. All right. So how are we going to prove this? We're going to prove this using the basis criterion. Okay. So we have to show that if I take this set S, which is the set of all tensor products, EI tensor Fj, where I belongs to capital I and J belongs to capital J. And if E is any vector space and F is any function from S to E, then I want to extend F to a linear map from the tensor product V tensor W to E. Okay. And I want to show that the extension is unique. Then by the basis criterion, this set will be a basis. Okay. So first, let's let S1 be the basis EI of V and let S2 be the basis Fj of W. Okay. Then we can define a function. Given our function F on this set S, we can define a function G from the Cartesian product S1 cross S2 to E, which is EI comma Fj goes to f of EI tensor Fj, right? I can define this function. Now, because S1 and S2 are bases of V and W respectively, if I have a function on S1 cross S2, then that extends to a unique multilinear map G tilde from V cross W to E. Okay. So that G tilde restricted to S1 cross S2 is equal to G. So how do you define this unique multilinear map? Well, G tilde is given by, so I have to define G tilde on an element of V cross W. So that is of the form summation alpha I EI comma summation beta j Fj, right? So if G tilde was multilinear, then by multilinearity, these are finite sums, right? So this would just become a sum over Ij, alpha I beta j, and then G of EI Fj, right? If G tilde of EI comma Fj is equal to G, then this would become summation alpha I beta j, G of EI Fj. So I can use this right-hand side as a definition of G tilde, right? I can use this right-hand side as a definition of G tilde. Is that clear?
Yeah, it's clear.
Right. So therefore, I get a multilinear map G tilde from V cross W to E, whose restriction to S1 cross S2 is G. Therefore, by the universal property of the tensor product, once I have a multilinear map from V cross W to E, that induces a linear map F tilde from the tensor product V tensor W to E, such that F tilde of V tensor W is equal to G tilde of VW, right? This is exactly what the universal property of the tensor product gives me, right? The map G tilde, the bilinear map G tilde, it factors as a linear map F tilde composed with the universal multilinear map, right? Okay. Yes, this is by the universal property of the tensor product. So, so in particular, this is true for all V comma W in V cross W. In particular, it's true for all pairs of the form EI comma Fj. So then I'll get that F tilde of EI tensor Fj is equal to G tilde of EI comma Fj. And that by construction is equal to G of EI comma Fj. And G by construction, G of EI comma Fj was equal to F of EI tensor Fj, right? That's how we define G. So therefore we get a linear map from the tensor product to E, which extends the map, the function F defined on the set S of tensor products EI tensor Fj. Is this clear?
Yeah, it's clear.
Yeah, okay. So F tilde restricted to S is equal to F. Okay. So we have a linear map extending our function on the set S. Now we have to show that this linear map is unique. Okay. So now suppose capital F from V tensor W to E is some other linear map such that capital F restricted to S is equal to little f. Okay. So then define a multilinear map capital G from V cross W to E by capital G of V comma W is equal to capital F of V tensor W. Okay. Then what happens on the set S1 cross S2? If I look at G, capital G of EI comma Fj, then by definition, this is capital F of EI tensor Fj, right? But capital F is an extension of little f. So this is little f of EI tensor Fj. And little f of EI tensor Fj is equal to little g of ei comma fj, right? So now capital G and little g, these are both multilinear maps which agree on pairs of basis elements, right? Therefore, by multilinearity, they have to agree everywhere, right? That means G has to equal G tilde, which is the multilinear extension of G, right? Okay. Is that clear? So let me just recall for you. G was the function on S1 cross S2. Ei comma Fj goes to f of Ei tensor Fj. And G tilde was, it's the unique multilinear extension of G, right? Okay. So if G is equal, capital G is equal to little g on pairs of basis elements, Ei, Fj, then capital G has to equal G tilde, right? By multilinearity. Is that clear? Yes?
Yeah, it's clear. Yeah.
I mean, two multilinear maps which agree on the pairs of basis elements, they have to agree everywhere, right? You just use the definition of multilinearity, so they will have to agree for all elements. Okay. So now capital G is equal to G tilde. What was capital G? Capital G of VW was capital F of V tensor W. So we get that capital F of V tensor W, this is capital G of VW. This is equal to G tilde of VW. What was G tilde of VW? This was F tilde of V tensor W. Okay. So then I'm getting that capital F composed with the universal multilinear map, this is equal to G tilde, this multilinear map, and also little f tilde composed with the universal multilinear map, that is equal to G tilde. But G tilde, this multilinear map, it has a unique factorization, right? As a composition of the universal multilinear map together with a linear map, right? So this linear map appearing in the factorization of G tilde, this is unique according to the universal property. Therefore, capital F is equal to F tilde. All right. Is that clear? Yeah.
Yes, it's clear.
Okay, so therefore S is a basis by the basis criterion, right? We've showed that any function on the basis S, on the set S, it has an extension to a linear map, and that extension is unique. So therefore it's a basis. Okay. Okay. So as an immediate corollary, we get that if you take finite dimensional vector spaces V1 to Vn, then the dimension of V1 tensor Vn is the product of the dimensions V1 up to Vn. Right? Is that clear? Because the basis will be given by tensor products of the bases of V1 to Vn, right? And this set, all the elements are distinct because it's a basis, so it's linearly independent. So all the elements are distinct. So this set will have cardinality equal to the product of the dimensions. Is that clear? Yes? Okay.
Yeah, it's clear.
Yeah. Okay. And you can also use this to say that V tensor, the field K, is isomorphic to V naturally. Okay, the map, the isomorphism is just V goes to V tensor 1. Okay, 1 is an element of the field K, so you can take this tensor product. So this map is an isomorphism because if I take a basis EI of V, that goes to EI tensor 1. And by the above proposition, EI tensor 1 is a basis of V tensor K, right? Because 1 is a basis of K. So the basis of V tensor K will be just EI tensor 1. Okay. So any basis goes to a basis. So this map is an isomorphism. All right. Is that okay? Yeah. Okay. Any questions? Okay. All right. So now let me look at multilinear maps from a Cartesian product of a vector space V with itself mapping into W. Okay. So let me call this space M sub K of V colon W. This is the set of multilinear maps from V cross V cross V K times to W. Okay. So these are called K multilinear maps. They're multilinear maps of K variables. Okay. Now, what I want to look at are actually multilinear functions. So those are, so this is bad notation, I'm sorry. There are two Ks here. Yeah, okay. So this K here is the field, and this should not have been a K, but well, that's a mistake I made. This K is meant to be the number of factors here, the number of variables. Okay. Okay, so if I look at the set of multilinear functions, then we can define a binary operation on multilinear functions in the following way. So if I have a K multilinear function and an L multilinear function, say alpha and a beta, then I can define a K plus L multilinear function, alpha tensor beta. Okay. So this is going to be a multilinear function of K plus L variables. So how is it defined? It's very simple. Alpha tensor beta of K plus L variables, V1 to Vk, comma W1 to WL. This is defined to be the product alpha of V1 to Vk into beta of W1 to WL. Okay, so alpha and beta both take values in the field of definition of the vector space. So in the base field of the vector space. So this product is in the field. Okay. So it's clear that this will be a multilinear function of K plus L variables, right? Okay, so we can define a tensor product of two multilinear functions. Okay. And using these tensor products of multilinear functions, we can give a basis for the space of multilinear L multilinear functions. Okay, so suppose V now is a finite dimensional vector space over a field K. Suppose EI is a basis of V, and suppose EI star is the dual basis of V star. Okay. So then if I take the set B, which is the set of all tensor products of multilinear functions, so the EI stars, these are linear functions. So their tensor products, L-fold tensor product, will be an L multilinear function, right? This will be an L multilinear function. So I take all such L-fold tensor products of these dual basis elements, okay, where my indices I1 to IL range over 1 to N. Then these tensor products, these form a basis for the space of L multilinear functions. Okay. And moreover, for any multilinear function T, we have an explicit formula for the expression of T with respect to this basis EI1 star tensor EIL star. the coefficient of this basis element is T applied to the basis vectors EI1 to EIL. Okay. And so T is equal to a sum over I1 to IL of these coefficients times these basis vectors. Okay. So is the statement clear?
Yeah. So the dimension will be n choose L, I suppose.
No, it will be n power L, right?
But then you'll have repeats, right? I mean, oh, okay, no, no.
you
So,
won't
so
have-
this,
no. These are
this
not
is not
symmetric,
alternating. Yeah,
right?
sorry.
This product is not symmetric. No,
Yeah, fine.
this product is not symmetric. No, this product is not symmetric. No. Yeah. So let's see, and you'll see in the proof, I mean, yeah, this will be a basis. So first of all, note, if I take L indices I1 to IL and another L indices J1 to JL in between 1 and L, if I look at EI1 star tensor EIL star applied to EJ1 to EJL, then by definition of the tensor product of multilinear functions, this is equal to the product P goes from 1 to L, EIP star applied to EJP star, EJP, right? So this is, so all of these are Kronecker deltas. So this product is 1 if and only if all of these are 1, right? All of the factors are 1, otherwise it's 0. So all the factors are 1 means that all the i's have to equal all the j's, right? So that means each I1 has to be J1 and up to IL has to equal JL, right? Okay. Yeah, otherwise it's 0. So that means that this tensor product, it takes the value 1 only on this L tuple of basis vectors. On any other L tuple of basis vectors, it is 0. Is that clear? Yeah. Okay. So now if I take a T, which is a L multilinear function, I define another L multilinear function T tilde, which is going to be the sum over indices I1 to IL, T of EI1 EIL into this tensor product, EI1 star tensor EIL star. The claim is that T tilde is equal to T. Okay. So why is that? That's because if I apply T tilde to any L tuple of basis vectors, EJ1 to EJL, then by what we've proved above here, right, these EI1 star tensor EIL star applied to EJ1 to EJL, this will only give me 1 if I1 to IL are equal to J1 to JL, and otherwise it will give me 0. So in this sum, only one term will remain when I1 to IL are equal to J1 to JL, and then this will give me 1, and this will become T of EJ1 to EJL. So that means that T tilde of EJ1 to EJL is equal to T of EJ1 to EJL, right? But then both are multilinear functions. So if they agree on all L tuples of basis elements, by multilinearity, they're going to agree everywhere, right? Is that clear?
Yeah, it's clear.
Right, just by multilinearity, you take any L tuple of vectors, you expand, write them with respect to the basis, then you expand using multilinearity. So if both multilinear functions take the same values on L tuples of basis elements, then they're going to be equal. Okay. So we get that actually T tilde is equal to T. So actually we've proved part 2 of this, that any T has this expression with respect to this set, right? It's a linear combination of these elements, EI1 star tensor EIL star. So that tells me that these elements span, the span of this set B is is the whole set of multilinear functions. Okay. Now I have to check that these are linearly independent, right? Okay. So that is also quite simple. If I have a linear combination, summation over I1 to IL, some coefficients alpha I1 to IL into EI1 star tensor EIL star equal to 0, right? Then I take a multi-index J1 to JL and apply both sides of this equality to the L tuple of vectors EJ1 to EJL. So as before, only one term in this sum will survive when the i's are equal to the j's, and that will give me alpha J1 to JL is equal to 0. Okay, so this is true for any L tuple of indices J1 to JL. Therefore, all the alphas are 0. And so that means that this set B is linearly independent. Okay, therefore it's a basis because we've already shown that it spans, right? Is this okay? Yes?
Yeah, it's okay. Yeah.
Yeah, okay. Okay. All right. So, so why were we talking about tensor products and then about multilinear functions? Well, it turns out that actually, if I look at V dual tensor itself, K L times, this is naturally isomorphic to the space of L multilinear functions from V to K. Okay. So here V, I'm assuming, is finite dimensional. Okay. So this isomorphism, when I apply it to what are called elementary tensors in the tensor product, so elements of the tensor product of the form alpha 1 tensor alpha L, where the alpha i's belong to V star, then phi sends this tensor product inside V star tensor itself L times. It sends it to the tensor product on the right hand side, which is the tensor product of multilinear functions. Okay. All right. So how do we prove this? So this is quite simple. The point is actually this space ML of multilinear L multilinear functions, this, well, one could show it satisfies the universal property, but we won't do it that way. But it comes with a universal multilinear map. It comes with a natural multilinear map from V star tensor V star cross V star L times. The map is just alpha 1 comma alpha L goes to alpha 1 tensor alpha L, where this tensor product is the tensor product of multilinear functions. Okay. So this map is clearly multilinear, right? And therefore, by the universal property of the tensor product, it induces a linear map phi from the tensor product of V star with itself L times to the space of multilinear L multilinear functions, such that T of alpha 1 to alpha L, T was this map here, is equal to phi of alpha 1 tensor alpha L, right? So that means that this property holds, right? Phi of the abstract tensor product, alpha 1 tensor alpha L, is equal to this concrete tensor product of multilinear functions, alpha 1 tensor alpha L, right? Is that clear? Okay. So now to show that phi is an isomorphism, we just see that, we just check that it sends a basis to a basis. Okay. So let EI be a basis of V, and EI star is the dual basis of V star. Then what does phi do to an abstract tensor product, EI1 star tensor EIL star? It maps it to the concrete tensor product, EI1 star tensor EIL star. And on the left-hand side, the set of these abstract tensor products, we've already shown, is a basis of V star tensor itself L times. And on the right-hand side, these concrete tensor products, we've shown that this is a basis of the space of multilinear functions, right? So a basis maps to a basis, therefore this map is an isomorphism. Is this all right? Yeah.
Oh, what do you mean by abstract tensor product and concrete tensor? Like,
Yes. So what I mean is, we have a universal multilinear map, right? From V star cross V star to V star tensor V star, alpha 1 to alpha L goes to alpha 1 tensor alpha L. So this is what I'm calling the abstract tensor product, right? Okay. It's just the universal multilinear map. Okay. This is the universal multilinear map. Right?
yeah.
And then what I'm calling the concrete tensor product is the tensor product of multilinear functions, right? So that is this multilinear map T from V star cross V star to the space of multilinear L multilinear functions alpha 1 alpha L goes to alpha 1 tensor alpha L. So this tensor product is what I'm calling the concrete tensor product, because I mean it's an element of some concrete vector space, not an abstract tensor product which is defined by a universal property. This space of multilinear functions is very concrete, right? You can write it explicitly. So this concrete tensor product takes values in the space of multilinear functions. Okay. All right. So
Yeah.
what we've shown is that what we've shown is the following, that if I take V star tensor itself cross itself L times, then I have these two maps One is the universal multilinear map to V star tensor itself L times. And the other is this map T to the space of L multilinear functions. And then we've shown that there is an isomorphism here, phi, so that this diagram commutes, right? Okay. So since on the left-hand side, this is a universal multilinear map, that also implies actually, because this map phi is an isomorphism, that will imply that this T, this is also a universal multilinear map, right? So phi isomorphism implies that T is also a universal multilinear map. Right. So here the point is we're getting a concrete realization of the tensor product as a space of multilinear functions. Is that clear?
Yeah, it's clear. Yeah.
Right. And we're getting an explicit description of the universal multilinear map. It is just
It's a
linear-
product of linear functions. Yeah.
It's the tensor product of linear functions. It's the tensor product of linear functions.
Yeah.
Yeah, so this abstract tensor product is having a very concrete realization. It's having a very concrete realization in terms of multilinear functions. That's all. Yeah. Okay. 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 Okay, so if this is clear, then let me carry on. So, okay. So I think one of the last things I want to say about tensor products is the following, that if VW are finite dimension, any questions? Sorry. Okay. So if VW are finite dimensional vector spaces over K, then the space of linear maps from VW, which I'll write as HOM VW, this is isomorphic to V star tensor W. And in fact, this is again a natural isomorphism. You don't need to choose a basis to define this isomorphism. Yeah. All right. So first, what we'll do is we'll work out what is a basis for the space of linear maps. Okay. So that's not hard to do. So you fix bases EI and FJ of VW and let EI star be the dual basis of V star. So then you define for each IJ a linear map Tij by Tij of V is just EI star V into FJ. Okay. So that means that this Tij, this goes from V to W, V maps to EI star of V into Fj. Right? Okay. So that means if I apply this to the basis vectors E1 to En, then all the basis vectors map to 0 except the ith one maps to Fj. Right? So that means the matrix of Tij with respect to the basis EIs and Fj, all the columns are going to be 0, right? The columns are just Tij of the basis vectors EIs, right? So all the columns are 0, except the ith column, the image is Fj, so that is represented as a column vector Ej, right? With 1 in the jth position. Okay, so yeah, so this is the ith column, and this is the jth row. Okay, so it's clear that these matrices, these form a basis for the space of matrices, right? Yes?
Yeah.
So therefore, these Tijs form a basis for the space of linear maps, right? Okay. Okay, yeah. So notice these are rank 1 linear maps, right? The rank of Tij is 1. Right? Okay, these are rank 1 linear maps, which form a basis for the space of linear maps. Okay. Now we're going to define a linear map from V star tensor W to Hom VW as follows. So first of all, notice there is a bilinear map from V star cross W to Hom VW. So how is this bilinear map defined? So suppose I have a linear function alpha on V. So that's an element of V star. And I have a vector W in W. Then this defines again a rank 1 linear map S sub alpha comma W, which is the linear map from V to W. V goes to alpha of V into W. Okay. So this is rank 1, right? It takes values in the span of alpha, in the line span by alpha, in the line span by W, sorry. Right? This takes values in the line span by W. Okay. So notice that this map from V star cross W to Hom VW, alpha W goes to S sub alpha W. This is bilinear, right? It's linear in alpha, you can see, and it's also linear in W, right? This S depends bilinearly on alpha and W. Okay. So this is a natural bilinear map. There's no choice of basis needed here, right? This is a natural bilinear map we can define. Therefore, by the universal property of the tensor product, this bilinear map, it induces a linear map, psi, right, capital Psi, from V star tensor W to Hom VW, right? Such that capital Psi of alpha tensor W is this linear map S alpha W. Is that clear? Yeah. That's by the universal property of the tensor product, right? So this linear map is defined without any choice of basis, right? It's a natural linear map from V star tensor W to Hom VW. Okay. But what does it do to a basis of V star tensor W? Remember, we showed that a basis of V star tensor W is given by a basis of V star tensor basis of W. So that would be EI star tensor Fj, right? So this linear map psi applied to EI star tensor Fj, this goes to the element of Hom VW, S sub EI star Fj. And this linear map is exactly the linear map Tij, which we defined earlier, right? Okay. So therefore, we've shown that the Tijs are a basis, and we know that these EI star tensor Fj, these are a basis. So therefore, this linear map maps a basis to a basis. Hence, it's an isomorphism. Is that clear? Yes,
Yes, it's clear. Yeah.
right? Okay. This is clear. So therefore, we have this identification between Hom VW and V star tensor W, okay, for finite dimensional vector spaces VW. And under this identification, this linear map S alpha comma W, this corresponds to the tensor product alpha tensor W, right? Where alpha is in V star and W is in W, right? Under this identification, S sub alpha comma W corresponds to alpha tensor W. And given any S in Hom VW, we can write it as a linear combination of these S sub alpha W's in the following way. I can write S as summation I goes from 1 to N, S sub EI star comma S of EI. Right, because if I apply this to any basis element EJ, what is this going to do? Well, these S sub EI star comma S of EI, unless I is equal to J, this will map EJ to 0, right? The only term which can be non-zero is when I is equal to J. And then when I is equal to J, you'll get EJ star applied to EJ, that is 1 into S of EJ. So therefore, this right-hand side, this sum will map EJ to S of EJ. So that means both the left-hand side and the right-hand side, these are linear maps which take the same value on all basis elements EJ. Therefore, they are equal. All right. So therefore, any S I can write as a sum over I, S sub EI star comma S of EI. And that means that any linear map S in Hom VW under the identification with V star tensor W, it corresponds to the sum EI star tensor S of EI. Okay. Is this clear? Yes.
Yeah, it's clear.
Yeah, it's clear. Okay, so we will use this much later in the course. But yeah, so this identification will be useful. Between Hom VW and V star tensor W. Okay. Excuse me. Okay, so so that ends more or less the linear algebra I wanted to do. So the next topic will be preliminaries on multivariable calculus and smooth manifolds. Okay, so okay, fine. So let me just excuse me, recall some basic definitions. So suppose T is a linear map between two normed vector spaces E and F. Then we can define what's called the operator norm of T, right? So this is defined to be the supremum over non-zero vectors V of norm of TV divided by norm V. Okay, so this is measuring this norm TV divided by norm V. This is the length of the image vector divided by the domain length of the domain vector. So this ratio is telling you how much T stretches the vector V, right? It's the stretch factor for the vector V. And then you take the supremum of the stretch factors. Okay. So this norm T is the maximum stretching of the linear map T. Okay. And this stretch factor, because both the numerator and the denominator, they are homogeneous in V. That means if I multiply V by a scalar lambda, then a mod lambda, this norm gets multiplied by mod lambda. So I can always rescale a non-zero vector V to make it of norm 1 without changing this ratio. So this supremum is the same as the supremum over the unit sphere, norm V equal to 1 of norm of TV. Okay. Right? Yeah. And then we say that a linear map between norm vector spaces is bounded if its operator norm is finite. Okay, so this maximum stretching is finite. And then we define the space LEF to be the space of bounded linear maps from E to F. Okay. Okay, so it turns out that if E and F are finite dimensional norm spaces, then actually any linear map is bounded between finite dimensional vector spaces. And that follows from the fact, which I won't prove, which is a well-known fact, that any two norms on a finite dimensional vector space are equivalent. That means that each is bounded by a positive constant times the other. Okay. So they give equivalent topologies on the vector space. And in finite dimensions, recall that boundedness of a linear map is equivalent to continuity of the linear map, right? And in finite dimensions, if you have a linear map from Rn to Rm, then it is continuous because each coordinate of the linear map is a linear function. So that's just some summation Aij xj, right? So that's a polynomial function. It's continuous, right? With respect to the usual topology on Rn coming from the L2 norm, right? That topology, like I said, is independent of the norm. So if you choose any other norm, it will still be continuous with respect to that. And so since the coordinates of T are continuous, T is continuous, therefore it's bounded. Is that okay? Yeah, any questions? And this is supposed to be a recap of, things which you've seen earlier. So I'm not doing them in much detail. So I'm just briefly recalling things. Okay. So what I want to talk about a bit to finish today is what are called differentiable maps between normed vector spaces. So maybe for that, I should draw some pictures and try to explain what is the derivative of a map in higher dimensions, right? So what is the derivative in higher dimensions? Okay. All right. So first, let's look at the simplest example. So suppose f from R to R is a differentiable function. So what does it mean to be differentiable? It means if I take a point on the graph of f, then for a differentiable function, the graph at each point is well approximated by the tangent line to the graph, right? Which has slope equal to f prime x naught. And in terms of the function, what does it mean about the function? Well, we know that f of x naught plus h minus f of x naught, this divided by h, this converges to f prime x naught. So this is equal to f prime x naught plus a quantity which is little o of 1, right? As h tends to 0. Right? So little o of 1 just means a quantity which goes to 0 as h tends to 0. All right. So if I multiply by h and rearrange terms, what that means is that f of x naught plus h is equal to f prime x naught. Sorry, f of x naught plus h plus f prime x naught into h plus a term h into little o of 1, that will give me a term which is little o of h, right? As h tends to 0. Okay, so these two are equivalent, right? Yes, this above equation and the below equation, these two are equivalent, right? Now, what is the second equation below telling me? It tells me that,
1 minute, that
yeah.
the term you were writing as order of 1. Hello.
Yes.
So the term you were writing as order of 1 is actually order of some h, such that that term eh by h, that norm goes to 0 as h tends to 0, right?
No, look, this is just definition of limits, right? If I order of 1 just
right.
means something which goes to 0, right? So this difference quotient,
Okay.
this is converging to f prime x naught, right? So that means that this minus f prime x naught, right? This minus f prime x naught, this goes to 0, right? This goes to 0,
Right,
right?
as h goes to 0.
So this is
okay.
equal to order of 1, right? Yes. Order of 1 just means something which goes to 0 as h goes to 0, right?
Oh, I see. So in that,
I'm just using the
Okay.
definition of derivative, right? This
okay, all right.
if quotient minus f prime goes to 0, that's all. Just
No,
nothing
I got
it's the
confused with
definition
the
of
term
derivative.
order of 1.
Yeah, it's just order of 1 means just something which goes to 0, right? So, okay, so now when I take this to the other side, multiply by h, I get this following equation, right? Okay. All right. So if you like, I can rewrite this as f of x naught plus h minus fx naught. This is equal to f prime x naught into h plus a term which is little o of h, right, as h tends to 0. Okay. Now, what is this? This is the change in f. Okay, this is the change in f, right? So this takes the value 0 when h is equal to 0. Okay. And what is this? F prime x naught into h. This is a linear function of h, right? Okay. And this order of h term, this error term here, this is small compared to h. Right? Okay. Yeah, so what are we doing? We're writing, so if I look at x naught plus h here, then this is f of x naught plus h here. So this much is the change in f, right? This is the change in f. And this much here, this is the linear function of h, right? This is f prime x naught into h. And what is this much? This much is the error term. This much is error, which is a little o of h. Okay. So what I'm doing is I'm approximating f near x naught by a linear function plus an error term which is small compared to h. Right? Okay. So this error is small compared to this vertical distance here, right? This. Yeah. And notice that this tangent line with slope f prime x naught, this is actually the only line so that the error term is a little o of h, right? In other words, if I take, this is my curve and I take the tangent line at a point, sorry, it's a very badly drawn line, but if I take, so for this tangent line, this error term, this is the difference between the graph and the line. This is little o of h. If I take any other line which is not equal to the tangent line, say another line like this, then you'll see that I will get an error term which will be a big O of h. It will look like a constant times h, right? Can you see that? Yes?
That's just any other line or what? Yeah.
Any other line which is not equal to the tangent line, right?
Yeah.
If I take any line which is not equal to the tangent line, right? Then see the difference between the two lines will be big O of h, right? Because they're two different lines. So the difference between the two lines will be a big O of h, like some non-zero constant into h. And the curve, the graph is within distance little o of h from the line. So therefore, by triangle inequality, the distance between this second line and the graph will also be big O of h, right?
Yeah, makes sense. Yeah.
Makes sense, right? I'm moving an amount big O of h from the second line to the first line, and then I can move up at most by a little O of h. So the error term will stay big O of h, right? Make sense? Yeah.
Yeah.
So what does that mean? That means that the tangent line is the unique line for which the error term between the graph and the line is little O of h, right? It is the unique line for which the error term is small compared to h. Is that clear? Right. So passing through this point, there are infinitely many lines with all different slopes, right? I could take this slope, whatever, all these slopes. There's only going to be one slope which matches up perfectly with the graph so that the error term is small compared to h. That is how you get the tangent line. It's the unique line so that the error is small compared to H. Is that clear?
Yeah.
Right? So geometrically, that's how one can think of the tangent line. Okay. So now that we have this formulation of differentiability, that the change in f, it should be a linear function of h plus an error term which is small compared to h. Okay. This we can generalize to higher dimensions. Okay, because see, in one dimension, of course, you can take a difference quotient, the change in f divided by the change in x, which is h. You can divide by h, but in higher dimensions, h becomes a vector. It doesn't make sense to divide by h, right? So this difference quotient becomes meaningless. Whereas if I write it in this form, in this second form, then notice that this term f prime x naught into h, this is a linear function of h, and any linear map from R to R is just multiplication by a scalar times into h, right? Any linear map from R to R is of the form T of h is equal to some constant lambda into h, right? For some lambda. These are all linear maps from R to R, right? Actually, what is this lambda? You write h as h into 1. This is T of h into 1. And then you take out h is a scalar, T is linear. So this becomes h into T of 1, right? So this is T of 1 into h. So this lambda is T of 1. Okay. Right. So actually we're writing the change in f as a linear function of h plus an error term which is small compared to h. Okay. Is that clear? So this generalizes to a map between normed vector spaces. Okay. So if f is now a map on an open subset U of a vector space E, a normed vector space E, taking values in a normed vector space F, then we will say that it is differentiable at a point x naught in U if there exists a bounded linear map T from E to F such that we have this, this formula here you can think of as a first order Taylor formula, right? This is a first order Taylor formula for F. So in general, we want F to satisfy a first order Taylor formula. F of x naught plus h is equal to fx naught plus a linear function of h, this bounded linear map T applied to h, plus an error term where, like we had in one dimensions, the error term was small compared to h. So in general, here we want the error term to be little o of h as h tends to 0. So now what does that mean? Now h is a vector and the error term, this is also a vector. This is a vector in F and h is a vector in E. So when I say that the error term is little o of h, what that means is that the norm of error of h divided by norm of h, this tends to 0 as h tends to 0. Okay. Is this all right? Yeah. So this is when we will say that f is differentiable. And notice that if this holds, if you have such a linear map which does this, then I can look at, for any vector h in E, I can look at what's called the directional derivative of f in the direction of h. That means I look at the line passing through x naught in the direction of the vector h. So that means points of the form x naught plus th. Okay. And I restrict f to this line, right? So restricted to this line, f becomes a function of a real variable, a single variable t, right? And so I can differentiate f with respect to t. So then it makes sense to look at this difference quotient, f of x naught plus th minus fx naught divided by t. So this is the derivative of f in the direction of h. Now, if I use this formula here, fx naught plus h is equal to fx naught plus th plus error of h. If I substitute this here, then you can see that this limit is going to be t of h. So let me just do that calculation for you to finish. So f of x naught plus th minus fx naught over t. So by the definition of derivative, what will this be? This is going to be the linear map t applied to th plus the error term of th this divided by t. Now this capital T is a linear map, so the t will come out here. So this will become t into th over t. So the t and the t will cancel. And plus, so t is non-zero. So what I'll do is let me assume this vector h is non-zero. Sorry, let me assume h is non-zero. So let me write this as norm h into e of t h divided by t norm h. Okay. If the vector h is 0, then this is of course identically 0. There's nothing to prove. This the limit is just 0. If h is non-zero, then I can write it like this. And then notice as t tends to 0, this ratio, the norm of this tends to 0, right? Because I know that norm of e of th divided by norm of th, right? This, by hypothesis, this goes to 0 as t tends to 0, right? So this term here will go to 0, right? This term, this tends to 0 in the vector space F because its norm goes to 0. And this term is constant, so the whole thing converges to t of h. Okay, so that means that this limit, which is called the directional derivative, nabla sub h of f at x naught. This is limit t tends to 0, f of x naught plus th minus f of x naught by t. This is equal to this linear map t applied to h. Okay. So this implies that t is unique if it exists, right? Because we have a formula for th, it's given by this nabla h f of x naught, right? Okay. And this t is defined to be the derivative of f at the point x naught. So the derivative dfx naught, this is defined to be this unique linear map t. So now what is the derivative? This is an element of the space of bounded linear maps from E to F. Okay. Okay, so in higher dimensions, what happens is the derivative becomes a linear map at each point. It becomes a linear map from the domain vector space to the range vector space. Okay, a bounded linear map. Okay, so that is what the derivative becomes in higher dimensions. Is it clear? Yeah. Okay, so any questions? Yeah, so we're out of time, so I'll say more about the derivative next time on Friday. Any last questions before we finish? Okay, so let's,
Sir,
yes, go ahead. Yeah.
will you give homework?
Exercises, not really homework, but probably exercises as we go along the course.
Okay.
Exercises here and there, yeah, just exercises.
All right.
Yeah, yeah. Some exercises here and there. Yeah. Yeah. Any question about the derivative? Okay, so let's stop today, and I'll see you Friday. Okay.